Hello, and welcome to video 14. In this video, what I want to talk about is something called inertia. This mass here is about a kilogram, about 1,000 grams, and it is connected to a bar at the top here. And what we're going to do is we're going to tug on this bottom string. And the question is, which of these do you think will break first? The top one or the bottom one? No, seriously, which one do you think is going to break? I don't want to do this unless you're into it. Would it change your answer if I did it quickly? Slowly? We're going to test both of those. First one I'm going to test is quickly, so I want you to think about that. Now, I'm not going to tug this with my fingers because I like them way too much. I'm going to use this rod instead. It feels no pain. So I'm going to tug very, very quickly, and we're going to see which one breaks. On the count of 3. 1, 2, 3. Interesting. Bottom one broke, no string attached, but the top one did not break. How many of you thought the top one was going to break? Well, I said we were going to test it both ways, so let's see what happens if I tug slowly. I've got more string. And we're going to repeat, but now I'm going to pull slowly. 1, 2, 3. And the mass fell. This one did not break. What was different? Well, clearly I pulled faster the first time, but why should that make a difference? There's a qualitative explanation I could give you around inertia. Inertia, if you remember, is the tendency of an object to resist a change in motion. So basically it wants to keep doing what it was doing. It was sitting still, minding its own business, perfectly happy in its existence, until I came along and exerted a force on it. That force was very, very large. For me to try to accelerate this mass means I have to accelerate it down this way very quickly, which requires a very large downward force. So if I try to do it quickly, this is going to resist that change in motion, and you're going to get a big force. It's much like even if you had a giant lineman on roller skates and you took a string and you yanked it quickly, you could break that rope. But if you pull very slowly, you can move them along just fine. It's similar here. So if you pull slowly, then this tension has to feel both the mass from here and the force you're pulling it. But if you pull very quickly, it's mainly going to feel just the weight, because this won't accelerate down that much because you've done it so quickly. By the time it actually gets going, you've already broken the string. But what about a little more rigorous explanation? I can tell some of you are clamoring. It's actually pretty straightforward. Whenever you have forces on an object, what you want to do is you want to draw something called a free body diagram that labels the forces acting on the object. In this case, we have the top tension, we have the bottom tension, so the top string, the bottom string, and then we also have the weight force. Now, because I'm trying to pull it down, I'm going to say that that is the positive direction. So what I want to do is I want to write Newton's second law. F net equals ma. Now, when we add up the forces going down are the bottom tensions pulling it down, the one that I'm pulling it with, plus the weight, which is mg, minus the tension, which is trying to work against the direction I'm accelerating in. And that's going to equal ma. So this is going to be the tension top. Now all I'm going to do is I'm going to bring this over. So I'm just going to subtract this. I'm going to get TB, meaning the bottom tension, minus the top tension, equals ma minus mg. Well, I'm going to factor out the m. M equals a minus g equals tb minus t. Well, okay, what does that mean? Well, what it means is if the acceleration, if I'm trying to accelerate that mass with an acceleration greater than 9.8 meters per second squared, it will have a positive net force down. Well, that's also going to mean that the tension at the bottom is greater than the tension at the top. So if the acceleration I try to give it is greater than 9.8 meters per second squared, well then the bottom tension is greater than the top tension, which means you're more likely to break the bottom string than you are to break the top string. Similarly, if the acceleration I give it is a little dinky one, if I just kind of push it real slowly, I don't try to accelerate it too much, don't try to rock the boat, the acceleration is less than g, that's going to mean the top tension is going to be greater than the bottom tension. So it's more likely to break the top string than it is to break the bottom string. In fact, if you pull slowly, the tension that's in here is equal to the weight force plus the tension that you're pulling with. So that's really kind of neat that we can explain that both qualitatively and by math, but it's going to be more fun if we go ahead and we do it just one more time. Maybe two more times. So if I take this string and put it like this, open this, I'm going to first pull slowly. And as you know, which one's going to break? 3, 2, 1. Well, that didn't go as planned. I think it may have actually untied. Well, now I'm down to one string. Do you want to do the top one or the bottom one? Bottom one? Okay. 3, 2, 1. And the bottom one breaks because of the large inertia of the mass. As long as I accelerate it greater than g. Very cool.